Hi everyone, in this video I'm going to start talking about rational functions. So as has been sort of the trend in these section 5 packets, the first little thing in your packet is kind of a summary of some of the things you should know by the time we get done talking about rational functions. I'm kind of all about here again working through some examples to make sense of this. So I would say after you've watched the videos and worked on this a little bit, just look back at this list and make sure you're really clear about everything. So I'll say really quickly what's going on here, but then by example, I'm going to try and show you these things. Okay, so first off, a definition of a rational function. We've got a definition of a polynomial, and a rational function is a polynomial divided by a polynomial. So we'll get some messy looking fractions. We've looked at some basic rational functions. So remember y equals 1 over x was one of our basic rational functions. And some of the really interesting characteristics are that these have both vertical and horizontal asymptotes. And we also looked at y equals 1 over x squared. The difference with that one being slightly different shape, but also that you don't get any positive. So that's y equals 1 over x squared, x, y. Okay, so let's see. So for starters, you should recognize the rational function as being something that involves some messy fractions, variables in probably top and bottom, but at least in the bottom. If there's no variables in the bottom, then it's just a numerical fraction and it's a polynomial again. So we'll get at this, but we want to learn how to looking at the equation for a rational function, just like we look at the equation for a polynomial. If we can get everything factored, we want to know where to look to spot the zeros, the x-intercepts of the rational function, when it has a vertical asymptote, and when there's a hole in the graph. That's a new one for this section, but they're pretty easy to spot actually. That's going to be our local behavior stuff. So this is the local stuff. So zeros, vertical asymptotes, holes in the graph. Those three things we'll look for all together. The global behavior is maybe slightly trickier than polynomials. There's a few different things that can happen, and this is all going to depend on the degree of p versus the degree of q. So if we have a cubic over a quadratic, then the degree of p is higher than the degree of q, and we'll have to use long division. This should say use. I'm seeing this us right here, to find the global behavior. So that's actually the last one we'll tackle. If the degree of the top is smaller than the degree of the bottom, so the top is say linear and the bottom is cubic, then you'll have a horizontal asymptote on the x-axis automatically, just like 1 over x. So this is 0 degree on the top, first degree on the bottom, so you get y equals 0. This is 0 degree on the top, constants are 0 degree, and second degree on the bottom, so y equals 0. An interesting one will be if the top and the bottom have the same degree, so say they're both quadratic, you'll actually get to look at the leading coefficients, the coefficients on the terms with the highest powers, and that will tell you where the graph will level off. So it will have a horizontal asymptote, it just won't be at 0. So again, I promise we will do all of these by example, but I want you to be thinking about that as two separate categories. So we'll look for all three of the things at the top. You could have zeros, vertical asymptotes, and holes in your graph. At the bottom, you can only have one global behavior. So you'll either have horizontal asymptote at 0, horizontal asymptote somewhere else, or some sort of slant asymptote or other global behavior. So keep this list in mind as we're working through, just to make sure that you really are looking for all of these things. Okay, so let's just go for an intro example. I'm going to do one that we can graph using transformations, and then we'll rewrite it in a form where we could use some of our other tricks similar to what we did for polynomials. So if I was using transformations, I would say I'm starting with that 1 over x shape. Y equals 0, x equals 0, and I'm just going to follow the easiest points, 1, 1, and -1, -1. The asymptotes determine a lot of this behavior, so just a couple of points to make sure I'm in the right spot will be great. So if you're getting, so this is the y equals 1 over x. If you're getting a 2 in the numerator, you would get that by multiplying the entire 1 over x function by 2. So this is a vertical stretch. And then the plus 3 is added to the end of the function, so that also affects y. It's a shift up 3. Okay, so I think that's not too bad of a pair to do together. So let's follow our horizontal asymptote first. If we do vertical stretch, it's away from the asymptote and it won't move. but the shift up will move it. So now we have a horizontal asymptote up at y equals 3. Okay, and then the vertical asymptote. Vertical stretch won't affect it, making an infinitely tall line twice as tall isn't really that impressive. And shift off also isn't very impressive. It goes forever, so we can't really tell the difference. So that stays at x equals 0. 1, 1, if we do vertical stretch, we're doubling our y, so it will go to 1, 2. And then if we shift up 3, it will land at 1, 5. So this is 1, 5. Negative 1, 1, if we do vertical stretch, it will land at negative 1, negative 2. And then if we shift up 3, it will land at negative 1, 1. Okay, so there's the shape I end up with. So again, sometimes we can graph these using transformations, but very quickly we get rational functions that are too messy to look at as just a transformation of a 1 over x or a 1 over x squared or even a 1 over x cubed or x to the 4th. So we're going to rewrite this in a different way. We're going to try and combine this and get a single fraction. And that's going to be the form that we start practicing with. So I need to multiply the 3 by an x over x, which means I get a 3x plus 2 over x. You don't have to switch the order, but I like the way that looks. Okay, so we want to be able to figure out key things about the graph. So what we won't get is, we're not doing transformation, so we won't be following specific points. But it's really important that we can figure out from this new form where our horizontal and vertical asymptotes are, and it's also important that we can get some other points. So usually what we'll do is find the zeros. When you have a fraction written, or a rational function written as a single fraction, it's usually not too terribly hard to find the zeros. So let's see, where do I want to start? Let's go ahead and talk about zeros first because I think they're fairly easy. If you want to find the zeros of something, anything, you set it equal to 0, right? So if we think about this, if we set this equal to 0 and we're trying to solve this equation, the first thing we would do is multiply both sides by the x, clear the fractions, and we just lose the x completely. So basically what I want you to remember is to make a fraction 0, you have to make the top 0. So the zeros of the top are the zeros of the rational function. So if the top equals 0, then f, we'll stick with the name we gave it here, is equal to 0. There is one exception to this. 0 over 0 is undefined. So if the top is 0 and the bottom is also 0, that we will discover shortly is when we have a hole in the graph. The 0 over 0 leaves a funny hole in the graph. But if the top is 0 and the bottom is not, so this is the first thing on our list, the rational function has a 0 at a0 if the top function is 0 and the bottom function is not 0 when you plug in a. So if the top is 0, we should have an x-intercept unless we have the weird case where top and bottom are both 0. So the top here is 0 if x is equal to negative 2/3. So if you can spot it, great. If not, set up your equation, 3x plus 2 equals 0, and solve. If you find yourself getting them upside down or messing up, just do that little bit of scratch work to make sure you don't mess up. Okay, so this is our 0. We only get 1. What else did I say I was going to look for? Vertical asymptote. Okay, so the vertical asymptote is happening at x equals 0. And if we look at this function, notice that x equals 0 is what makes the bottom 0. So in general, if the bottom equals 0, you probably have a vertical asymptote. Again, the one exception is if the top and bottom are both 0, then you're not having zeros or asymptotes, you're having a hole in the graph. Okay, so let's see. What am I trying to say here? So if x equals 0, so again, I have the graph here, so I'm kind of using that as a cheat. But basically, even without the graph, what we're trying to get at is if you can look at this and see when the bottom is 0, that should give you a vertical asymptote. So what's happening there is if x is 0, it's undefined, so we should not have a point on the y-axis, and we do not. If x is really, really small positive, so 0.01, 0.001, 0.0001, when you divide, so let's see, the top is going to be pretty close to 2. 3 plus, say, 0.03 or 0.003, so a little bit bigger than 2. When you divide a number like 2 by a tiny, tiny number, dividing by tiny numbers makes your fraction big. So if this was 1,000th, when you divide by 1,000, that's the same as multiplying. When you divide by 1,000th, that's the same as multiplying by 1,000. So it makes this really big. So tiny, tiny positive denominators make your fraction really big. Tiny, tiny negative denominators make your fraction really big negative. So that's why we're getting that off to plus or minus infinity. And then right at the point where your denominator is 0 is where you get the vertical asymptote. Again, with the exception being if the top and bottom are both 0, you'll get something different. And we will talk about that when we see it. The horizontal asymptote is the other thing we want to be able to spot just by looking at the equation. So for this, I would really emphasize what it means to be a horizontal asymptote. It's not like a vertical asymptote. It's a different thing. The vertical asymptote happens because the denominator of fraction is getting really small, and it's making the fraction blow up and get huge. The horizontal asymptote is really just telling you global behavior. So horizontal asymptote is your global behavior. Okay, so what you should really be asking yourself when you go looking for global behavior is what happens when your x's are really big positive or really big negative. So if we look at this fraction right here, let's imagine that x is 1,000,000, or you could do 1,000,000,000, or pick a big number. If you plug in a big number to this fraction, so if I'm plugging in 1,000,000, I get 3,000,002 on top, and I get 1,000,000 on bottom, which is really, really close to just being 3. So what happens is that if x is huge, huge number, this 2 becomes pretty negligible. It's there, but the bigger x is, the less this has any influence on the fraction. And what we get is just this 3x over x behavior. So this is going to have a horizontal asymptote at y equals 3, which is exactly what we found up above. This is just a different way to find it. So looking back at our list, this is the scenario 2. If the top and the bottom have the same degree, so here, linear top, linear bottom, first degree top, first degree bottom, then what happens is you have to really get into it and say, okay, well, if I compare the top and bottom, if I pick out those two terms with the biggest power that happens to be the same, that's why we're looking at this, the rest of the stuff becomes negligible. Those biggest powers take over when I plug in really big numbers, so it's going to behave a lot like a 3x over x, which is just 3. So if the degrees are the same, look at the coefficients. That's the only time you look at the coefficients. Okay, so this is going to be our strategy. So we'll go in opposite order. We'll try and pick out all of this info, and then we'll try and put it together and make a graph of a rational function. As we go here, you'll see some examples of what the graphs look like, but I would just say in general, on the left and right hand sides of your graph, you should see shapes really similar to this. And then if you have multiple vertical asymptotes in the middle, you can get shapes that look like little U's, or shapes that look kind of like a cubic, except it's got asymptotes, upside down or right side up. So we'll see very specific shapes over and over again, and that will help us as well. So kind of like polynomials, part of this is just familiarity with what the shapes generally look like, and then picking out some details using this strategy. All right, thanks for watching.